Hello, everyone, and thank you for joining us today. Welcome to day 2 of Megger's Virtual Cable Best Practices Seminar. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentations and supporting you on any technical issues or questions for our presenters. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of each presentation. Today, we will have 2 separate presentations with their own Q&A sessions, so please stick around after our first presentation concludes. The presenters today are Marshall Bird, Cable Sales Manager, and Henning Oetjen, Product Manager for the cable products. Our panelist today to assist with the Q&A session is Robert Probst, Product Manager for Cable Products. All right, let's go ahead and get started with a brief overview of our seminar today. Thank you for joining us today, Marshall.
Thank you. Welcome to the webinar. And I'm Marshall Bird, and so I will present a portion of today's best practice session. And then as Michael explained later, Henning Oetjen will also do part of the presentation. And before I jump into the agenda, I would just like to make a comment that we're going to cover a lot of material during this presentation. And because of the width of material, we won't necessarily go into great depth. But anything that we don't reach in detail, you can always reach out to us later and ask for a tailored, customized webinar presentation specifically for your needs. Well, let's go ahead and get started. Today's agenda, first, I'll talk a little bit about medium voltage cable types. We'll talk about the different types of construction and how this applies a little bit to cable fault locating. We'll look at common underground infrastructures, and this is important because different infrastructures require different techniques and different tools. We'll talk a little bit about cable fault failure mechanisms, how these underground cables can be damaged and how they can fail. And then we'll talk a little bit, a quick review of some of the common cable fault locating tools. And after this short introduction, then we'll hand off the presentation to Henning, and he'll dive into a little bit of detail on some three-phase industrial circuits, networks, branched manhole systems, and some of the tools and techniques specifically for those type of infrastructures. And then at the end of that, we'll have a question and answer session. And after the question and answer session, I'll pick back up and I'll go over some URD fault locating infrastructure, and again, some of the techniques and tools used. And then we'll finish up with a final question and answer session. So let's go ahead and get started. We'll look at medium voltage cables, and you'll notice medium voltage shielded cables. So what we're talking about for most of this presentation is a shielded cable. And the reason that's important is because many of the techniques that are used for fault locating are specific to shielded cables. And in the North American market, these shielded cables commonly come in a 15, 25, or 35 kV class ratings. And if we just basically go through the cable itself, we have a conductor, copper, aluminum, covered by an inner semicon, and then we have the main insulation. And the insulation could be EPR or XLPE. Those would be the common extruded insulations that we would see today, followed by an outer semicon, and then of course the shield, the neutral concentric itself, and then the jacket. And these medium voltage cables come in different construction types. We just talked about the single phase shielded medium voltage cable, but you could also have a 3-core conductor where one cable has 3 conductors in it, and each of those individual conductors has its own shield. And then if you look down at the bottom of the screen, you'll see a belted cable. It looks similar to the 3-core. We have 3 conductors, but there's only a single common shield. And when Henning goes into his presentation, he'll probably dive into a little bit more detail on these different construction types. And as mentioned, EPR and XLPE are common insulations that we see today, but there's still quite a bit of paper lead insulated cables out there. And the reason I kind of highlight that with these 2 pictures is these cables have been around for a long time. They're still out there, and they do require some different techniques and troubleshooting applications versus the solid dielectric extruded cables. All right, let's look a little bit about, or talk a little bit about underground infrastructure. When I was preparing this presentation, I found this interesting drawing from back in the early 1900s. Shows an intersection. I believe this is in New York somewhere, Broadway and Fulton. But even back in 1890, there was extremely complex underground infrastructure. And of course, this has a huge bearing on the type of tools and techniques that we use. So if we look at underground infrastructure, we can kind of roughly break it into 2 different areas, what we would call, a networked, a branched, a manhole system. I commonly call these systems, downtown network systems, and they come in different flavors, but some of the things that are common in these type of systems is the complexity. A network, a branched, a manhole system. Here we have on the right-hand side, or the left-hand side, a picture of multiple conduits and cables. It can be a very complex environment. And if we look at the picture on the right-hand side, even in a trench environment where we've exposed some of the underground infrastructure, it can be extremely complex. Lots of different utilities. You could have all different combinations here. Then if we move to a URD system, in some sense, these underground infrastructures can be a little bit simpler, perhaps characterized by the classic green pad mount transformer in someone's front or backyard. If we look at some very simplistic diagrams of these URD systems, you could have something as simple as a simple loop feed, which is relatively easy to troubleshoot and to move the normal open for power restoration. However, the URD systems, they can get somewhat complex. Over on the right-hand side, we show a more of a radial design with kind of a tap or branch configuration. So the URD systems, while in general they're simpler, they can have some complexity to them also. One of the other ways we can divide URD systems is whether it's direct buried or some form of conduit. And this has implications for troubleshooting and fault locating. If we have a direct buried cable, when we talk about fault location, what we mean is we pinpoint the fault, we dig up the faulted cable, and we repair it by putting a splice in. If we have a conduit system, in most cases, you isolate down to a section and you pull and replace. You pull in a new section of cable. Okay, so if we move on to some cable fault types, the failure mechanisms in medium voltage cable. And this slide, we use this slide a lot when we talk about test and diagnostics on how you can examine a cable, but it also applies to how cables can fail. And so we can start with, termination, a pothead, and elbow. Many times, if the termination fails, it can be traced back to a workmanship issue. And if we look at joints or splices, kind of the same thing. When we take new cable and we put a splice in it, when we work on it, if the splice or termination isn't isn't assembled exactly to manufacturer specs, we might introduce a weak spot in that termination or splice that will eventually lead to a fault. We can also have weak spots in the cable itself. And these type of weak spots, that you could have a manufacturer's defect right from the manufacturer. That's not very common in today's high quality cable, but it could happen. We could damage the jacket or sheath when we install that cable. And if we nick or damage the jacket, we could have water ingress, and over time that could lead to a fault. And again, when we pull in the cable, we could exceed the bending radius, or we could over pull it, so we could cause some type of mechanical damage. So if we look at these failure mechanisms, we're talking about workmanship, installation, mechanical damage, this type of thing. Then if we look at the insulation itself, over time, the insulation itself can degrade and fail. And when we dive into this, we talk about water treating, aging of the insulation on the solid dielectric cables, on the older PILC style the cellulose itself, the paper, can degrade over time. So long story short, there's all different ways that a cable can fail, many of them related to workmanship. And I guess just as a side note, we do use this same slide when we talk about test and diagnostics. And many of these types of failures, there is possibility to discover them with some type of test and diagnostics. So that does play a part in maintaining your cables. Okay, so if we move on to some equipment, one of the most common pieces of equipment that you would use in troubleshooting cables would simply be a cable locator, cable tracing, cable location. And in its simplest terms, you have a transmitter that injects a signal onto the cable, and then you can trace that signal in the ground with a receiver. And this helps to verify cable path, and that can be very important in a troubleshooting and fault locating scenario. Another important piece of auxiliary equipment, if you will, is the cable identifier. This device allows you to select a particular cable amongst many. So maybe you have an open trench with 3 cables, and that's what the top of the picture shows. And we can put a clamp, a sensor around each of those exposed cables, and one of them is going to have the signal that we're looking to identify that particular cable. If we look at cable thumpers, when most people think about cable fault locating, this is what they think about. They think about a thumper. And so this is kind of the core tool, if you will, that is commonly used for many types of fault location. And of course, thumpers come in all different sizes. Here we're showing some medium size to large systems. Over on the far right-hand side, we have a little baby thumper. And we'll talk some more about these thumpers. But one of the key things about thumpers today is when we start talking about fault locating sequences, some of these thumpers have built into them a fault locate sequence to help the operator move through and find the fault quickly and efficiently. And the earlier slide showed portable thumpers. There's versions of these that can also be mounted in a truck or trailer. The picture on the left-hand side shows a fairly large thumper mounted up into a trailer. You can see the radar up above it and a fairly long cable reel on the right-hand side. And then the picture on the right shows a truck mount thumper that's not yet installed. It's being prepared to be installed into a truck. Another piece of very common equipment is a TDR. We're showing the display screen here of a TDR. The radar, the time domain reflectometer, this tool is used to get a distance to the fault. a distance to the end of the cable. Sometimes you might get distances to splices or transformers, but basically this is your, excuse me, this is your distance device to help you identify, to prelocate where the fault is down the cable path. And also on the right-hand side is a pinpointing device. Now, I'll commonly call this a listening device, but that's really not correct. It does have a headset, and with a headset, everyone recognizes, oh, I can listen to a fault. But a modern pinpointing device does much more than just amplify sound in the ground. If you look closely at the display on that, it says 66.7 milliseconds. That's how far away the operator was from the fault. So this can basically give you a distance to the fault, and we can display that in either how long it took the sound to get to you in terms of milliseconds, or if you want, you can even put that into a footage measurement where it'll tell you how many feet away you are from the fault. And then let me finish up in terms of equipment with an example of an integrated test fan. And an integrated test fan, I use the term integrated to indicate it has fault locating equipment in it usually. So it would have a thumper, a radar, and you could have the auxiliary equipment off to the side in the van. But many times these vans also have test and diagnostics equipment. So you would have potentially a VLF, a partial discharge, a tan delta. You could have some combination of these test sets side by side with the fault locating equipment. And this is important in the overall scheme of things. Rather than just troubleshoot and repair the cable, you have the option with an integrated system to also do some diagnosis, determine what type of condition the insulation is. Are there any future problems with terminations, etc.? And as you go through the test and diagnostics routine, if you have a cable that fails under test, you have the fault locating equipment to quickly figure out exactly where the problem is. Okay, so that's just a quick review of the equipment, and I'm going to pause here and we're going to switch it over to Henning's presentation where he's going to dive in a little bit further on the underground infrastructure.
All right, Henning, I'm going to send control over to you right now. You ready?
Yeah.
All right, here we go.
Okay. Okay, so thank you for attending this this webinar. We call this a best practice seminar, and it's a little bit different than our typical webinars because a best practice seminar is really there to give you an overview over the state of the art of different technologies and methods. And so it is, like Marshall was already saying, not necessarily always in depth in every detail. So what we like to encourage is if you have certain questions afterwards, or you like to explore certain topics in more detail, we are very glad to provide another, let's say, maybe more detailed webinar, specifically custom to what you would like to discuss. So when we look at, and I'm looking at the three-phase scenarios here, and so we have basically two types of three-phase scenarios. One is what I would call the three-phase high-load industrial circuits, which also includes wind farm circuits. And these are typically characterized by, the industrials maybe 2,000 to 5,000 feet. The wind farms can go much larger, much longer, maybe 50,000 feet. And most of the time, all these circuits have either XLP insulated cables or EPR insulated cables. There is very little paper cable involved in these industrial circuits. Typical system voltage is 35 kV, and typical conductor sizes range from 350 to 1000 MCM. Could be also maybe sometimes 1200 or 1500 MCM, depending on the load. So when you look at what this really does is the length of the cable and the conductor size affect the cable capacitance, and that is one of the parameters we need to understand when we do fault locating later. So the cable capacitance on these cables per phase is typically between maybe 0.5 and 5 microfarad. 0.5 is the shorter ones, and 5 would be a long wind farm type cable. Most of the time in these type of circuits, the cable segments can be isolated, and that is very important because when I have isolated segments of cable, my fault locating procedure becomes a whole lot easier compared to when I have one piece of cable that is, like we had in one particular incident with one wind farm, was 26 kilometers long, right? And then fault locating becomes very difficult. So on the next slide, I show you just very briefly a circuit diagram of a three-phase. You see here the three-phase on the left side, and then you see branching off the three-phase, some single-phase and so on. But the important thing is that these can be isolated. They are either switchgear or typically involved, so it can be all isolated, and that is very, very important. And on a side note, the old wind farms, some of the old wind farms, they couldn't be switched around. They had all T-splices in them, and it became a nightmare to fault locate. And today in wind farms, we typically have sectionalizing or switching cabinets also, so to make that aspect a whole lot easier. And the most important thing, fast, much faster. Okay, so whenever we do fault locating in three-phase systems, we have to pay really attention to make sure that when we fault locate on one of the phases, that the other two phases, if they are energized, they don't backfeed unknowingly somewhere into the phase that we want to fault locate. So there has to be some checking done to make sure that if there are any backfeed points, that they are open. Okay, so when we do fault locating, it's always good not just to go out and hook the thumper up and pray for the best. It's good to do some screening. And so what can we do in terms of screening to learn more about the type of fault we have? Because in the end, the type of fault determines what fault locating method will work best to find that fault and to find it in the quickest possible way. So one of the tests is we perform a insulation resistance test, let's say maybe at 5 kV, each phase to ground. And so we analyze the results, and look for that the results will fall in 3 different categories. Either we have a fairly high insulation resistance, and high, I'm saying above 100 megohms. That would typically indicate a good insulation resistance. Even some of the solid dielectric cables, they could go much higher. But so this is on the lower end really of the solid dielectric cables. But what we have to keep in mind, even a high reading doesn't mean that this cable is fault-free. Because remember, we're only testing maybe at a 5 kV, we have a 5 kV insulation resistance tester. So all we know is that at 5 kV, it has a good insulation resistance. So to really, when we get a high reading, we must afterwards perform a high-pot test on that same cable, and we must perform it at the peak of, at least at the peak operating voltage. And what that means is, if I have 35 kV circuit, 20 kV phase to ground. That's RMS. So if I only use 20 kV DC to high pot, it's not going to be good enough because my peak volt is 28 kV. So I have to at least test up to 28 kV DC to see whether that cable has a issue. And even then, if that turns out to be good, it's not the ultimate answer whether the cable is good or not, because if I had an open conductor, I could even have a much bigger gap, which would require even a higher voltage than the phase to ground. The phase to ground voltage, peak voltage, is only good for basic pinhole faults. They will find those, or they will indicate that I have that type of a fault. But if I have an open conductor, and you will see there is one other test that we will do in a moment that will then close the loop. And with that test result in, I can make a final decision whether a cable is good or not. So it is several steps involved. Many times, somebody does a insulation resistance test and reading a sign says cable is good. Well, it might be, but it could also not be. And so be careful about this. So the second category is when we have insulation resistances, maybe between, I'm using here 500 kilo ohms and 1 mega ohm. So that is typically indicating I have a high resistance fault, or basically what is a high resistance fault is a pinhole fault, and a pinhole is an air gap. So I have a flashing air gap, and that's why it's high resistance. So it builds up voltage to the breakover voltage of air, and then it flashes over. And then I have sometimes faults that are much lower in resistance, less than 100 kilo ohms, and I have seen faults that are maybe 2 kilo ohms, 5 kilo ohms. And when we have those type faults, we have to be very careful, because sometimes these faults will not flash over anymore because they have so much leakage current that it cannot build enough voltage up to really flash over. And the other issue with those faults is we might have to limit our thump energy. And you might think that is a very strange thing to suggest, but why do we do this? Because if we have a fault that is very low resistance and I put dump enough energy into it, it could happen that I make that low resistance even lower to a not completely short circuit, but close to a short circuit, which then I will have a big issue finding pinpointing, because a short circuit fault is much harder to pinpoint than a flashing fault. So, but there are telltale signs as we go through the process that will suggest to us which way we have to go. And that is why it's so important to do some of the screening tests up front. Okay, so what I also can do is I can use the TDR, and you heard Marshall was saying the TDR is a distance meter, and that is what many people see as the benefit of the TDR, and that is certainly the case. But the TDR is in essence really not a distance meter by definition, it is an impedance meter. And it shows impedance, and it shows really impedance differences along a cable. A good cable would have no impedance change, so it's a flat line on your screen. And anytime you see some wiggle on the screen, that means it's either up or down. It means a higher impedance or lower impedance than what the characteristic cable impedance is. Many cables in these distribution cables are 50 ohm cables. And so if you had, suddenly a spot where you only have 10 ohms, you would see a downward blip. If you have suddenly a spot where you have maybe 150 ohms, you have an upward reflection. You still see the end of the cable, however. That is important, okay? So why do we do this? Because we can do, again, with a TDR, we can do a phase comparison. So we connect phase to ground like we would normally do, and we can compare the three phases to each other. And what we're really trying to identify with that test is we're trying to find out whether we're really looking at the true cable end, because and that can be verified. We can do a absolute positive test to make sure we can see the cable end, because that excludes the other two possible findings, a short circuit and an open circuit. If we see the cable end, then we cannot have a short circuit and we cannot have an open circuit. If we cannot verify the cable end, then we might have a short circuit or an open circuit in the cable. And the distance to those is where that short or open circuit is located, which means there shouldn't be a open or short circuit in any of these cables. That means most likely that's where a fault is, okay? It's an indication, a first indication that there's something wrong with the cable if we cannot ascertain the true end of the cable. Okay, we can also do with the TDR a different comparison test, and that is a face-to-face test. Not the face-to-ground, but the face-to-face. And the face-to-face test on a three-phase circuit has one big advantage. What it will really tell us beyond any doubt whether we have somewhere an open conductor. If I do a face-to-ground test with the TDR and I get an open, it could be an open neutral, it could be a cut cable, or it could be a open conductor, one of the three. When I do the face-to-face test, I get an open. It can only be an open conductor, and that is very important to know. When I fault locate, I have an open conductor. Okay, so really, what that test does, the face-to-face test, it measures the impedance differences between the phase conductors, and wherever there is an impedance difference, it doesn't have to be a complete open. It doesn't have to be a complete short circuit. Just a difference in impedance shows me that there must be a difference in the conductors. And whatever difference there is means there is some damage to the conductor, because if the conductor is fine, I wouldn't see that difference in impedance. So in a way, that difference in impedance between conductors is an indicator where most likely there is a damage or a fault. Okay, and I will show you a slide here where you exactly see this. Okay, this was a 345 kV pipe type cable out of a power station, generating station, and it was pipe type is filled with oil, 3 phases in the pipe, in the steel pipe, filled with oil under pressure. It had failed, and so when I tried many different things and couldn't really make ends meet, and then I said, okay, let me do the phase comparison. Okay, and you see here on the right hand side, you see the big open, so that was the end of the circuit. Actually, the circuit went out underground from the power station up a hill on the switch yard, and then it went on overhead line out. Okay, so it was about I think 8,000 or 9,000 feet underground section up to that switch yard. So when I did this phase comparison, you can see the green line and the purple line, right? And you see clearly there is a difference. And so the one is lower impedance than the other one. The other one is pretty straight, so it probably has no problem. But the blue one certainly has a problem because it's not supposed to have a different impedance here. So what we did is, this was the indication to start looking, and in this case, little luck on your side is always helpful. We looked on the map and we found that distance was the first manhole out from the generating station. So we opened the manhole and I said, well, let's try, maybe we can thump it. And we were lucky, it did thump, and it was right in the splice, in the first splice in the manhole. So I'm just saying, but the indication to find that spot was through the phase comparison method. It's a very powerful tool when you have a multi-conductor cables or multi-conductor circuits. Okay, so what are the typical faults that you have after going through the pre-screening? What are the typical faults we expect in three-phase, circuits with solid dielectric cables? It's pretty flash. For the most part, those are flashover faults, high resistance faults. Okay, and the most common fault locating method today is the in prelocating that we do a prelocation in these circuits. And why do we do a prelocation? Because the prelocation gets us an approximate distance to the fault, and what it really does, it reduces the thumb time that we need when we have to pinpoint. Typically, once you have a distance from prelocation the pinpointing shouldn't take much more than maybe a few minutes to really narrow it down to an area of about a square foot or maybe 2 square feet. So most circuits can be sectionalized by various methods. Okay, I mean, many of these circuits have fault indicators installed, so we have already a pretty good idea where to look. But we can also, and I think Marshall eventually will talk about sectionalizing method in URD loops. So I mean, that same technique could be also used in some of these circuits. That allows us also, because most circuits allow us to isolate individual phases. That's very important because you will see the difference when we talk about network systems where that is not always the case. But in these circuits, we should be able to isolate individual phases, which again makes it a whole lot easier to fault locate. And so these circuits present really a point-to-point scenario. The TDR is a very good tool to apply to point-to-point fault locating scenarios. And that's what we have for the most part in these type circuits. So I will show you here the prelocation methods. We typically use 2 prelocation methods. One is what we call the arc reflection method, using the TDR. And TDR stands obviously for time domain reflectometer because it measures the reflections in the time domain. And that allows us with a velocity to calculate the distance. It's not a distance meter, it's a timing meter, so to speak. But known velocity, we can calculate the distance to the fault. So with the arc reflection method, we get at the fault a negative reflection, because when we put the high voltage on at the pinhole, we get a little arc. The arc shorts out the center conductor to the shield, and when at the very same time we shoot in the TDR pulse sees a short circuit and will show a negative reflection. That's what you see on the right hand picture here. You see the blue trace is just the TDR trace by itself, so no high voltage. It shows the end at 449 feet. And then in the second step, we do the same thing. We repeat it. We repeat it, but using also discharging the capacitor. It flashes over and it makes that TDR pulse reflect negatively. And where the impedance mismatch is, see, up to that point, the 2 traces are identical and they're split up, and that's our fault distance, 257 feet in this case. Now, so if you look at this process of arc reflection, we have to create a flash over first, and then we have to shoot in the TDR pulse, and everything has to happen at the right time. It has to be synchronized, so the TDR pulse sees an arc. If the TDR is too fast, then it will not see an arc because the arc hasn't developed yet. It doesn't see the fault. If we shoot in the TDR pulse too late, it can also not see the arc because the arc has already extinguished and we don't see it. So you need the synchronization. Sometimes for certain faults, but especially sometimes on paper cables, that is much more difficult to do. And for those situations, we have another method. We call it the ICE method, or the current decoupling method, which is using a TDR, but not as an active TDR where we send out a TDR pulse. We're using merely the TDR as a transient recorder, like a scope. And so we use the thumper, we thump it, the cable at the fault, we get a flash over, and so we get now the flash over occurs between the conductor and the concentric neutral. So we basically getting a signal on the neutral, which forms a standing wave between the fault location and the capacitor inside our unit. And you can see on the left-hand side, you see it is this curve. It's pretty much looks like a sinusoidal curve, but it's a curve that has repeated peaks in it, and the peaks all have the same distance, and the fault distance equals the peak distance. So we see here we have 735 feet, but like I said, because it's a standing wave between the fault and the capacitor inside the unit, we will have to subtract the test lead from that distance. If we have a 100-foot test lead, that means that fault is 635 feet out. So these are the two basic methods to do a pre-location for flashing faults. That's very important to understand. If I have a non-flashing fault, they don't work, and I need different method, okay? But for flashing faults, and in these type cables, like I said, solid dielectric cables, for the most part, we have flashing faults. These are the two typical methods being used today. Okay, so once we have established a pre-location distance, now we can do the pinpointing. And we do pinpointing clearly when this is a direct buried cable, because we need to know where to dig the hole. But even if we have cable in conduit, it is a very good practice to do a pinpoint, because it confirms the result of what the pre-location method did yield. And because I have, like Marshall was saying, typically I have to cut the cable, and I don't want to cut the wrong cable segment. So it's always good if you have a chance to verify a pre-location result with a pinpointing result. It's a very good practice, regardless whether in conduit or not in conduit or direct buried. So in this case, Marshall was already mentioning a little bit what we strongly advocate as the best pinpointing method really is what we call the coincidence method, and we call it in a more common term lightning and thunder, and you all can relate to this very easily. Because when you're in a lightning storm, you see the lightning, you start counting 21, 22, 23, 24, 25. You hear the thunder, you stop, and you say, okay, so it's 5 seconds divided by 5. That means it's 1 mile away. That's how this method works. So it basically measures the time for the sound to get to you, because the thunder, or in our case, when we fault locate, the electromagnetic pulse from the flashover will travel with the speed of light. We cannot even measure this. But we can measure the speed it takes, or not the speed, but the time it takes for the sound to get to us. And so you can say this type of pinpointer is like a stopwatch. If you look at this gentleman down here on the far left side, where he says 66.9 milliseconds. So he has a stopwatch, and it has two sensors, the electromagnetic sensor and the acoustic sensor. And when it picks up the electromagnetic pulse, it starts the stopwatch. And when it picks up the acoustic, it stops the stopwatch, and it gives you the timing. And as he moves closer to the fault, obviously the time gets lower. So that's the indication in which direction you have to move. You have to move in the direction of lower numbers. And once you over the fault, you at the lowest number. And once you pass the fault, you see numbers go up again. It's a very simple principle, but it's a very excellent principle, because it doesn't rely purely on the sound. Whenever you rely only on the sound, there are many things that can go wrong, and it's not a very efficient method to just acoustically try to locate a fault. So with that, I like to switch now my presentation and go to the three-phase downtown branch network circuits. And again, a couple parameters of them: 5 to 20,000 feet, sometimes 40,000 feet. We're working with one customer has 100,000 feet, but that's out of the ordinary, right? But most of these circuits are in that range. And originally, because these downtown systems, they are the oldest systems. They are much older than any URD system, because they go back to the end of the or early 19th century, right? So they are really old systems. And because of their really old systems, they have many times still paper cable in them. And when you have paper cables, Marshall mentioned already, there are two types of paper cable, belted and unbelted. So the reality is, in many of these systems, you have a mix of cables. You have old paper, it could be belted, unbelted, or both. And you could have spliced in with EPR and XLP. So you have really a mix of different type of installations. And that's important to understand. And then we have a conductor sizes typically. Let me just. Excuse me. This stupid MSN. Okay, I'm sorry. So we have. No, I'm on the computer, but I cannot talk. Okay, so we have in these systems, like I say, a mix of different type cables, and the voltage is typically only 13.2 or 13.8 in these systems, and so pretty much all these cables are 15 kV class cables. The typical conductor size is between 350 and 500. Sometimes you have also 1000 MCM. Again, it depends on the loads. And but what's really very different about these circuits is they have typical branches in them. And these branches, in many cases, cannot be isolated. They are hardwired T or Y splices. And that makes fault locating a totally different ballgame. In addition to it, we also have most of the network transformers that are used are delta transformers. And again, they could be hardwired or they could have switches in them. And I talk about that in a moment a little bit more. But whether they are hardwired or they have switches, again, makes a difference what we can do in terms of fault locating. Okay. And I had planned for a circuit diagram on the next, and you see only placeholder. Unfortunately, I was not able to secure that map, that circuit map, because of some proprietary concerns. So, but anyways, I think most likely any of you who have worked in downtown network systems, you know exactly what I'm talking about. And I will later show basically a rendering of my own on a system like that, but a much more simplified diagram. Okay, so so now what's really important is that we understand the type of transformer we have. And you see here, this is a board, underground board. You see the network transformers in them. And like I said, we have two types hardwired in the circuit. So it's always in the circuit when we're performing fault locating or also cable testing. And that means the phases cannot be isolated from each other. And there are other systems, other transformers where you have three-way switches in them. And I try to indicate this here. You have 1, 2, 3 phase. You have here the delta transformer, and you have here the switches. And the switch has 3 positions. Obviously, an operating switch when the transformer is cut into the circuit, then you typically have a grounding position, and you have, and that's the most important for us from fault locating point, we can open the transformer. So if you see here in this diagram, if I open the transformers, now I have 3 individual cables, and I can actually fault locate on A phase, B phase, or C phase. If I don't have those switches, I cannot do that. Okay, so interesting. Why isn't it moving? Okay, now it's moving. Okay. All right. So we need to apply some general considerations when we do fault locating on three-phase branch networks. Okay. One of the things is very important. When I say always, I never say always, but for the most part, you always want to start at the substation to fault locate, because that is from where the circuit was fed when it failed. So we need to look at the entire circuit from the substation going out to the multiple ends in that circuit, because a branch network system has probably, I don't know, 40, 50 ends basically, right? So another thing that's very important, all network protectors must be open, must be confirmed open, because I cannot have feedback from network transformers to the circuit I wanna fault locate in. Most of the time today that is done via SCADA operations. So in the old days, one had to go out to every transformer and make sure that the network protector actually opened. Okay. Then I have to look at the from going out from the substation. I normally have a, like what we call a substation getaway, and that can be a cable that could run maybe from a couple hundred feet, but could also be maybe 1,000, 2,000 feet to the first, let's say, either branch point or to the first network transformer. So it makes sense to look at that section differently, because that is a true point-to-point fault locate. And so I can use the same methods that we just described on the industrial type circuits. And that's the benefit of using a TDR for that portion of the network. And you have two possible outcomes. Either you find a fault in that section, then you home free, very good, and it didn't take much time to find it, or there is no fault in it, and that means you can exclude it. You don't have to pay any more attention to that long section of cable, and you can move on to the real branch part of the network. So that's, if the fault is in that branch network part, the TDR-based methods are useless. And why they're useless? Because, like I said before, the TDR is an impedance measuring device, so it measures impedance changes. Now you can see in a network, I have a lot of splices, and I have transformer terminations. I have all this stuff in, and every time this is associated with an impedance change. So I have a jungle of impedance changes, and because every impedance change really constitutes a reflection of part of the radar energy. That means if I have enough of those impedance changes and reflections, my radar pulse is running out of steam and I don't see anything anymore. So that's why typically we say in a branch network that the benefit of the TDR is very, very limited. I always say, maybe in 20% you're lucky, because if you just happen to have the fault pretty close to where your connection point is, you will see the fault. But this is not a method that is typically used. On the other side, to just try it takes you maybe 2 minutes to see whether you see something that looks meaningful. If it doesn't, you move on and you do whatever you do normally. Okay, so there's nothing lost. There's only something to be gained, because if you see the fault, the time savings is tremendous compared to a traditional fault locate in a branch network. Okay, so also what's important to recognize in these type of networks, we don't need to know the exact fault distance, because we're looking for the faulted cable segment between two manholes. So the distance is not that critical, and so what's also important is, obviously, if we can switch the transformers in that open position, we should always try to do that, because that allows us to isolate individual phases in the system. I just talked to a customer a couple of months ago, and they used to do that all the time, which made their fault locating very efficient, but at the expense of the time to make sure that the transformers were in an open position. And because they had a fairly old system, they had to basically go to every transformer and manually check that this happened. So management in the end decided it's too much of a time loss of time. So we better off leaving transformers in and trying first to see, and only if we cannot find it, then we might have to do that step. So, there's always a compromise. It's always depending on what the specific situation is, what is the best solution. One other point that's really very important and sometimes gets a little forgotten is the bonding in these network circuits. In the old days, in every manhole where you had a splice, you had a grounding rod, everything was bonded, was perfect. Today, in many cases, there are no grounding rods anymore in the manholes, or they're abandoned or not replaced because they're so old. But why is bonding important? Because the method we will use looks for basically a current signal, electromagnetic signal. And if we don't have good bonding, what could happen theoretically, just to make the point, is you sending a pulse out, it flashes over, and that same pulse comes back on the very same cable. So you have a pulse in one direction and a return pulse in the opposite direction. And when you measure the signal, you measure the difference between the two, and there is no difference, and you measure nothing. Now, you always will measure a little bit, but you can see it could be that you measure a very low signal, which makes it very, very difficult. So the better the bonding in the system, you eliminate this issue. And some of you might have used there's a unit in the market, it's a very nice unit. It's called the X35. It's an above the ground underground meter. You don't have to open manholes. You can pick up this electromagnetic pulse above the ground. But you can see that makes it very nice and convenient. You don't have to go in manholes. You don't have to pump manholes out and to do all this good stuff. But because you do it above the ground, the signal is already reduced. So you need a very high sensitivity signal unit, to pick the signal up. Now, if you have a poor signal, it could be that the unit won't pick up anything. And that's what I hear sometimes. People say, well, we use it, sometimes it works and sometimes it doesn't work. That is a clear indication of the bonding condition in your circuit. So I just want to point that out. It's not, it's not equipment. Every piece of equipment has limitations, and it's designed for certain things to do. Okay, so what is another screening test now? After we going through some of the considerations, what is a screening test we can do? Again, we can do a insulation resistance test just to get a feel for the insulation resistance, because really when we have a fault, typically we expect to get a low reading, or a lower reading than a good cable has. But the fact is, if we know how low it is, it will tell us. If we have, let's say, in the extreme case, we would have a dead short, we would have no resistance, which normally doesn't happen. We always have maybe, the lowest I ever saw was about 500 ohms. So that's low, okay? But if you have a high reading, that means you have a good chance to get a flashing fault, okay? So, and the same things apply if you have a really low resistance fault. It might not thumb, and if it still thumbs, you will be very careful how much energy you dump in that fault, and not the old-fashioned way, crank it up so you get more oomph, okay? That might be just the worst thing you can do in that situation. So the insulation resistance gives you an indication where you are, okay? Now we can also do, because I mentioned we have in these circuits many times we have paper cables, so we have belted or unbelted cables. And the belted cables, like I said, they don't have their own neutral on each conductor. So that's why we also do the insulation resistance not only face to ground, but we also do it face to face. Because if we had a face to face issue and we only testing face to ground, we might not see it. Okay, we might not see it. Sometimes you see it both ways. Okay, but again, you want to fault locating is a procedure where you want to exclude whatever you can exclude, because then in the end there's only one or two things left, so you have a good idea what the problem is. And so a negative result is also a very positive result in terms of fault locating. Okay, so when we do a face-to-face, again, the readings are very similar. You know, on paper cable, you know, paper has lower insulation resistance typically than solid dielectric cable. So you see, I lowered the number down to 50 megohms for a good resistance. So if you have a high reading, that means either you have no belted cable or you have no face-to-face problem. One of the two. Okay. Now, if you have a lower reading, face to face, that means there is something going on between the phases. But in addition, since we did the face to ground before, we also can look at the face to ground results and see whether that face to face translates also into a combination of face to face and face to ground issue. Okay. And again, if we have really low readings, then we have to be very careful how we, you know, in terms of how we apply energy to that fault. Okay, so when we another screening practice is, besides doing the insulation resistance face to face and face to ground, we can do now the same thing again with the TDR to measure the impedance differences. Okay, and again, it's for the face to ground. We do it for the same reason. We want to see whether we see the true end of the cable. If we can do it, like I said, in a network system, you have a lot of reflections. It might not work very well. I mean, all these TDR things I'm talking about right now, they might not work that well. But we can give it a shot, because if we see something, it's a very valuable result. Okay, and we can also do face to face comparison, like I was explaining on the industrial circuits. But overall, you have to keep your expectation low on using a TDR in these branch network systems. So it pretty much defaults back to the insulation resistance test. Okay, and just to give you one example, I had once a situation where, you know, customer was pretty yeah, I don't want to say desperate, but they were really trying to figure out, they had a fault in the network, and it gave them a lot of grief, and they had an issue to really go to the substation because it was very hard to reach. So they tried it from one of the ends, and but they were lucky because they were able to isolate put the transformers in the open position. So they actually had 3 phases. So I said, okay, do an insulation resistance test. So they did it face to ground, and everyone was low. Everyone was low. And then I said, well, do also the face to face. Everything was low. So I said, that is highly unusual that everything is low. That means almost suggests that you have one spot where everything just completely blew up and is shorted out to each other. Okay. In the end, they went to the substation and they found, I think it's called a reactor, that was right in the substation that had caused a short circuit between all phases. Okay. So that's why I'm saying the insulation resistance reading gives you a good indication, and the fact to go from the substation can save you a lot of time. Okay, so all right. So now, what are the typical faults in these systems? Okay, typical is a blowout fault, pinhole fault, high resistance fault, which happens typically in the straight sections between manholes. And then you can also have obviously splice failures, okay, in the manholes, at the Y splices, at the T splices. And, you know, typically in these manholes, you have a lot of water, you know, it's not a very pleasant environment to work in. And, you know, the cable itself, the cable type, whether it's paper or, you know, solid dielectric, can also have an impact on the fault and how to find it. And like I said again, belted cables can show face to ground and face to face faults. Okay, and you see here again this photo on the right hand side. You see a belted cable. You see each face has paper insulated, and then but not every insulation has a concentric neutral over it. There's only one concentric neutral. That is that copper tape that you see under the lead sheath, which acts as the neutral. Where on the left side you see every face has its own concentric neutral. Now, obviously, this is not a paper cable, but it doesn't really matter. This is a XRP cable. Okay, now just to, you know, probably you have all seen this, you know, on the left side, you see a typical blow up in a manhole, and you see all this white tape. This is normally tape that's protection to prevent fires from catching onto other cables when one cable blows up. And it did a good job here. And then you see the congestion in the manhole that Marshall was already pointing out. So these are very complex manholes. And, you know, Marshall mentioned one tool. He talked about the cable identifier. That is sometimes a very, very important tool to even figure out when you're in the manhole, where's this cable coming from, where's it going to, right? So you're really on the right cable when you do your fault locate, okay? And then on the right-hand side, you see a typical manhole with a lot of water in it, okay? So most manholes I see, you know, a lot of water in. Okay, so what are the typical methods to fault locate? We call it the current method, or in the more colloquial jargon, chasing the fault current. Because, you know, there's one thing about the fault current. Fault current will find the fault. You know, we cannot see the fault current, so we have to find a method that we can detect the fault current, and that is what we use a galvanometer for. So by putting a coil on the cable, and when we thump, we get a current pulse, and with the galvanometer, we can pick up that current pulse, and we see the direction in which we have to go. And so the idea is, I don't go to every manhole. I go only to the Y or T branches, open the manhole, put my coil on the cable that incoming to the splice, and make sure I see a signal. That means the signal is still coming into that splice. And then I put it on the two outgoing cables. And in one cable, I will get a signal, and in the other cable, I will not get a signal. So I know, okay, I have to make a 90-degree turn here because my fault current is going that way. And then you go to the next Y splice and do the same thing. So you leapfrog from manhole to manhole, but only those where you have Y splices. And that is you know, some people don't like it too much because they think it's too time consuming. But I would say this, from what I have seen is, on average, you save time doing it. There might be sometimes you get really lucky and you can hear a fault with a second method that I call here out as the acoustic method. You can, I will not deny that. But many times I have seen the opposite, where you cannot pick a good acoustic signal up and you just scrambling and cannot make ends meet. So this method to chase the fault current is a systematic approach that will get you to the fault. So let's talk about that. And you know, the good thing is it works for flashing faults or non-flashing faults. Even if I had a short circuit somewhere, when I put my thumper on, that current still goes through the cable. I still can pick that signal up, okay? Very, very important, because the acoustic method If I don't have a flashing fault, I hear nothing. So I can forget about it. Aside from the fact that it's sometimes very hard to locate the acoustic signal. You know, people go down in the manhole, they listen in the conduit, they try to really do all kinds of things. It's not a very, it's a hit and miss approach. I have to say that way. And it's not systematic approach, okay? And it works only on flashing faults. And like I say, the TDR method for the most part is not applicable, but I always say try it first, because you can do low voltage TDR gives you impedance differences between phases, which, like in the example I showed you, gave me the indication where to look for the fault, which is very powerful. Or basically low voltage means it's non-flashing faults. Or if I do arc reflection, I can do flashing faults. But again, you know, arc reflection is very, very difficult to do on these systems. So these are the three methods. And here's, you know, my network diagram, and you can see there are quite a number of manholes in it and branches in it, and you can see the fault is there on the lower side between the two last manholes, and you can see the red framed manholes are the ones I have to analyze to see where my fault current is going. Okay, and so that is a way. It is very, very straightforward, and I get a good, even if I have the bonding is not so well, I still get a good signal because I measure the signal right at the cable. I have to put the coil onto the cable, which is on the other side the disadvantage, because I have to open the manhole, and typically I have to pump the manhole out, which can create some other issues. Okay, so that is the method to really the best method in terms of a systematic approach to find the fault. Okay, and you see here, you know, two different devices, and you see the coil here. You know, this is a device. It's we call it impulse detector, which picks up the you know, the signal, and this is a coil, and you put it on the cable. This, you can adjust the gain on this, and on the right hand side you see the coil. This is purely a galvanometer, no battery unit. It's purely a galvanometer instrument that doesn't need any power, and you see the what they call the tick on the needle, and you know which direction you go. It's the same on this one. Now if I can gain up the signal, I can see a larger swing, but it's very dangerous, because if you change the gain as you go further out away from the location where you connected, you can create big issues for you that you're chasing the false signal. Okay, so typically we say once you set the gain at where your thumper is connected with the unit in the left, then you do not touch the gain anymore. Okay, because it just makes a small signal is better than the wrong signal. Okay, so all right, one other quick aspect of thumping and energy and noise and all these good things. You know, many of the old thumpers were network thumpers, were single stage thumpers. Many of them had a rating of 25 kV surging, and you know, there might be 7,500 joule. And you can see this. This is a curve that is this blue diamond shape you see here. It's 7,500 joule at 25 kV. But you also see when you talk to people in the old networks, what voltage do you thump at? Normally people say, well, I don't want to really go much beyond 10 kV because it's only 13.8 and it's old, and you know, I'm concerned I thump this cable to death, because you might have to thump longer time, right? Because it will take some time to fault locate, you know, using this method. So, and you can see if I go down in voltage, I go to 10 kV, how many joules do I have left? Maybe 1,200 joules, right? So that's a big cry away from the 7,500 joules that the nameplate says. So 1,200 joules is much less. It's much less noise than what I would get at 7,500. But I cannot use 7,500 because it'll destroy my cable, right? So that's the old saying, you know, the surgery was very successful, but the patient is dead now, right? So we don't want to do this with network cables. All right. So that's where, in contrast to it, you know, today you have more and more multi-stage capacitor thumpers, and you can see you have here an 8, 16, and 32 kV thumper, and if you look at that, you see we have absolute less energy than at the 7,500 joule from that thumper, but we have 3,500 joule. But you can see we have 3,500 joule at 4 kV, 8 kV, and 16 kV and 32 kV, right? So if you look at where you typically thump, you have much more energy available and what does that energy do really? More energy typically makes a louder bang, gives you a better fault image if you can do arc reflection, and it gives you also a better indication on your galvanometer. It gives you more of a tick. And why does it give you more of a tick? The energy, you can say, you know, is the same, but why does it make a difference whether I have, let's say, 3,500 joules at 16 kV or 3,500 joules at, let's say, in this case, I'm using the 4 kV? Because when you go to the next slide, that explains it. It's, you know, it's energy. The energy is the same, but if the voltage changes, something else has to change. Energy is watt seconds. Energy, watt seconds means volts, amps, seconds. It's like your kilowatt hours you buy from the utility, right? So it's electric power times time. Okay, and what the difference is, even the energy is the same, the time that the power flows is longer at the lower voltage. You can see here, if I go 8 kV at 3,500 joule, I have 4.5 microseconds. And if I go with the big thumper, the big old thumper, 7,500, and I go to 8 kV, I have only 0.96 microseconds. So the flow of that energy is much, much shorter, and the energy is actually much less, okay? So that is why a multi-stage thumper is normally advantageous to be used in these applications, because I can better adjust the energy that I want to apply to a safe voltage to operate in my network system. Okay, so maybe as a finishing slide, you know, these are general performance recommendations for fault locating equipment for three-phase circuits, whether industrial or network type systems. You know, the surge generators, which are an essential part of any fault locating equipment. There should be preferable multi-stage units, 2-stage at least, 3 or 4-stage, depending. The surge voltages should be between 25 and 32 kV, but with multi-stage, so you also have, you know, lower voltage stages. The energy should be not less than 1,500 joule, and you know, 5,000 joule is a pretty good number to have, especially if you have 5,000 joules at maybe 8 kV or 16 kV. Okay. Burn feature, okay? Many people are swearing by burning faults, and there has to be a little bit of caution that needs to be applied, because if I burn solid dielectric cables, I normally shoot myself in the foot. Because what happens when you burn a solid dielectric cable, you set the whole insulation material on fire, which means it smokes away. And that fault will be afterwards, you will not be able to thump it anymore. So it's a totally different issue when I have paper cable, because paper cable, I have oil in it, and I need to lower the fault resistance so I can thump it And that means I have to burn the oil, literally burn the oil and make from the oil carbon. So I have no carbon, and carbon has a lower resistance, so I can thump the fault. So burning is a good feature when I have paper cables. And like I was saying before, it all comes together when I have a mixed cable circuit in a network, and I do the high pot because I get a high insulation resistance. I said you have to do a high pot, and if I get a high pot where it fails maybe 20 kV, that is not a plastic cable. That is, or not a solid dielectric cable. That is in the paper section. So if I know it's in the paper section, then I can also much more freely use a burn feature, because a burn will only occur at the fault location. Some people are concerned. They say, "Oh, so much current." Well, let's put this all in perspective. We use maybe a good burner has maybe 500 milliamps, maybe a 1 amp. We make some burners that can do up to 20 amps. But if you really look at that current is nothing compared to the normal operating current on these cables, okay? So the current itself cannot damage the conductor. But when you have a low resistance fault, it will do a lot of damage there, okay? And that's the whole intention. It should condition the fault so I can thump it, okay? All right, so going on here, moving on, when we go to the fault locating itself, to the prelocation, it's very clear an inductive type arm filter is absolutely preferable over a resistive type filter, because any resistive type filter will suck out the energy that the thumper provides. So I use a big thumper with a lot of energy, and then I put a resistive filter in, so I'm defeating my purpose. So it should be a inductive type filter. If I use a TDR, and like I say, I would always recommend in a network fault locating system to have a TDR. In industrial systems, you need it anyways for prelocation, but it should have a range between 25,000 and 100,000 feet, okay? And it should have a very simple phase comparison feature built in, not one where you have to, store and recall and overlap and do all this. Whenever you make it too complicated, people will not use these type of features. Even they're good features, but they're too complicated. And then last but not least, you need a good pinpointing device. And it should be the combination of electromagnetic and acoustic coincidence technology that will give you the best results overall for pinpointing. So I think this is was my last slide. So I think we will go to
question and answer session. I'll take it from here. All right, wonderful. So Henning has knocked out his presentation for our first segment, so we're going to jump into our Q&A session. You guys have been throwing some great questions our way, and I want to jump into them as soon as possible. We have a lot to get through, so the first one I'm going to ask is going to be directed towards Robert Probst. Robert, is there any danger to the thumper equipment if the cable is too long? Oh, Robert, I think we might have you on mute still. All right. While we figure out Robert's audio real quick, I'm going to jump over to the second question, over to Marshall. Marshall, what would be the length of cable you would recommend? Okay, a little bit of feedback. What would be the length of cable that you would recommend installation isolation points for fault location?
Well, the answer to that is it depends. Obviously, we've talked about different types of infrastructure, and for fault locating, it is nice to have isolation points. It can make the job much simpler. But to fully answer this question, you would need to know specifically exactly what type of infrastructure you were talking about. In general, the isolation points make it easier to sectionalize and troubleshoot the system. So it would be a balance, between the cost of those installation points, how often you're going to fault locate, et cetera, et cetera.
Maybe I like to add to it. Obviously, on the other side, you want to minimize the number of splices you have in the cable, right? And most of the time, if possible, you try to use a full reel of cable between these points, if you can. That is typically on medium voltage cable, maybe 2,000 feet. Now, if you in a city block, sometimes you cannot use 2,000 feet, then you have to have shorter cables, right? But you know, it's clearly the advantage not to have too many splices in, right?
All right, perfect. Let's try and get Robert back on real quick. All right, Robert, you with us again?
How about now?
Wonderful, excellent. All right, rolling right in. Is there any danger to the thumper equipment if the cable is too long?
Well, the short answer to that regarding the medium voltage world is no. There's typically no danger because the thumper, or let's say cable fault location equipment, the system, has a discharge unit, and that is well sized for the energies that you can face on typical medium voltage cables. Now, when the question is if the cable is too long, when we go into fairly long offshore cables and stuff like that, the energies can be substantial, and that is the reason why all of those systems are designed around a very special high power or even ultra high power discharge unit, which can handle that. In those cases, a normal medium voltage thumper or fault location equipment would not be enough anymore, because if the cable is charged and then something happens and it discharges through those off-the-shelf commercially available thumpers, the unit would be destroyed. So on very long cables, you need additional discharge capabilities.
Well, there might be one other part to this question, if I understand it correctly, because if the cable is too long, that I interpret this as, well, maybe it's a cable that has an extremely high cable capacitance. And typically what we have to do is when we fault locate and we use a thumper, we have to sort of match the cable capacitance to the capacitance in the surge capacitor. At least there has to be a certain ratio between the two numbers. And so if that ratio is not given anymore, then you could have a situation like you're using a very small, I call it the baby thumper on a wind farm cable, right? And maybe the voltage would be enough to find it, but the capacitance is so low that you never get a flashover. And then it becomes a problem if people keep on trying to get a flashover, that what they're actually doing is they're charging the cable up a little bit more every time from the surge capacitor in the unit, put a little bit more energy in, a little bit more energy in, and eventually the whole unit will blow up because the cable discharges into the unit and blows it up. So that's what we do in our units now. We have a clear message that shows if that happens, if the unit doesn't discharge, it recognizes this and says, either you have to increase the voltage or you need a higher voltage thumper, one of the two things. But you don't want to keep thumping if you don't see a discharge. It's very easy to see because the needle doesn't go down, you're not discharging, and that's a warning signal in the flag to do it. Now, like I say, our units, they will prevent you from doing that because the software will recognize it and stop the thumper. Okay.
Thank you, Henning.
Okay.
Robert, what causes a difference in impedance values in the cable?
Well, the impedance is mainly determined by geometry in this case. And so that means anything that is, kind of changing the geometry of the stuff that comes out of the factory, right? What is delivered on the reel. So you have the end terminations, splices, transformers, all of these things. But just to make this clear, I mean, in cable fault location, we're after impedance changes, okay? So don't confuse this with a value in ohms or something like that. We want to see the trace with the changes in impedance, and anything that has an effect on this geometry is kind of an impedance mismatch and will cause a reflection. And that reflection goes back to the radar, and then you can see it in the trace. So anything like, as I said, a splice, end terminations, if you have these Y-grounded single-phase transformers in these loop circuits that you have in North America, so all of that is an impedance change and will show up on the trace.
Great. Thank you, Robert. Henning, can you provide an estimate of what % of faults cannot be detected with a 5 kV Megger test set when comparing three-phase measurements?
I mean, that depends. Is that a, it depends also a little bit on the type of circuit. Is it a 13.2 circuit or is it a 35 kV circuit, right? I mean, on a 35 kV circuit, if I use a 5 kV unit, I think that's really on the low side, right? If I use it on the 13.2 circuit where I have 8.7 or 8.2 or whatever that number is, I think it's even a little less. I have a better chance to see it, but you cannot really. The only way to exclude that problem is if you get a high reading. If you get a low reading, you know the answer. It's bad cable. If you get a high reading, you have to do the high pot at the peak operating voltage. That is my best advice to you, because to try to estimate and guesstimate, you're just making fault locating a nightmare, I think.
Thank you, Henning. Robert, what decay method is used for fault location?
Okay, so the decay method is a so-called transient method, okay? So it does not rely on the TDR being an active measurement device. It's similar in nature to ICE, which, Henning also explained. So decay is used when you have faults that can where you're able to still charge the cable. That is one big difference between decay and ICE. So if the cable is chargeable, then decay can be applied. That excludes quite a few types of faults already, because if you cannot charge the cable anymore, then decay cannot be applied. The other thing is the method is only effective when you have a fairly high breakdown voltage, fairly high flashover voltage, because it has to do with the energy. The decay uses the fact that you can charge the cable up, and that energy then helps you getting the signal that you need. So if you have high resistive faults with high breakdown voltages, which is also typically the case on transmission cables, long offshore cables, all of these things. And on a more, let's say, equipment side, whenever your fault resistance, the breakdown voltage exceeds what your thumper, your cap discharge device can do, then you can try to use decay. We just recently had an example in Hamburg on a paper cable where the cap discharge did not go high enough, so we kind of made a workaround, and we got it to work with decay, because we would charge the cable, and the decay, because it uses the DC high pot, went higher, so we were able to still find the fault.
Maybe if I just may add to this, you're basically using the cable as your thumper capacitor. That's what you do, and that's why you need to get enough charge into the cable, and you only get enough charge into the cable if you can go high enough in voltage. It's the old equation, energy equals half C times the voltage squared. So the voltage squared, you go high in voltage, you get quite a bit of energy into a cable. Let's say if you have a 69 kV cable, and so you have what is only 42 kV face to ground. So it's probably on a higher cable. If you had a flash over voltage of, I don't know, 60 kV, you can see you can get a quite a bit of a substantial amount of energy in that cable if it flashes over at 59 kV, right? So, but if you have a cable you can only charge to 10 kV, you get no energy in that cable, so decay is totally useless. Okay.
Great, good deal. I think we have time for one more question before we jump into the next presentation with Marshall. So, Henning, can we use phase comparison for low and high resistant faults?
Well, a phase comparison you cannot use for low resistance fault. Yeah, depends how phase comparison between phases that have a difference in impedance. You can, okay, because you have a something to compare to. If you had a single phase cable, then you can only see a dead short or an open. You need a complete open or complete dead short to see it. You cannot see because you cannot compare to anything else. But if you have three phases, then you can use low voltage. You can see low voltage faults, but you cannot see high resistance faults with the TDR, right? Because it cannot measure. If you have a pinhole, the TDR cannot pick that impedance change up, right? So that's so the phase comparison method, we use it many times in low voltage cables where you have many low resistance faults. It's a very good method. So for low resistance fault, it works excellent. For high resistance fault, it cannot work by itself. But again, if you can do the face-to-face, the conductor-to-conductor comparison, that's a very powerful tool again. Okay.
All right, excellent. Marshall, are you ready to regain control for your presentation?
Yes.
All right, here we go.
Okay, can someone verify my screen is up?
Yep, we are on slide 43 in the presenter view. You'll just need to flip that around for us, and then we'll be good to go.
Okay. All right,
All right, perfect.
is that correct now?
You're green for go.
Okay. Let's just jump back in to some more infrastructure discussion. We're gonna flip away from the very complex branched network type systems and go back to talking about URD systems and some of the techniques and tools that we would use on URD systems. And you saw this slide earlier. Many times in the North American market, a URD system could be a simple loop feed or some type of a radial with taps and branches. And if we sort of start at the very beginning, before we talk about fault locating on a single individual cable, we might want to consider the troubleshooting process, the power restoration, getting lights back on. If we have a basic loop feed like this, we basically have 4 tools to figure out where the problem is and do power restoration. One tool that's always available but not recommended would be to divide the circuit and close in with a fuse. And if the fuse holds, then the fault is past where you divided the circuit, and you just continue that process until you eventually isolate the fault. It's a very harsh way to, customers don't like it, you're blinking their lights. The system doesn't like it because you're pulling fault current. A second tool that can be used is fault indicators. If you have fault indicators installed, and if they trip properly, that tool can very quickly get you down to the area of the fault. A third tool to get lights back on would be to use a high-pot stick attachment or high-pot unit where you isolate each section of cable one at a time. And in essence, you determine whether or not it does or doesn't hold voltage, and you continue that process till you find the one that doesn't hold voltage, and now you can isolate that and restore power. There is another way to do it. We're talking about cable fault locating equipment, But you can use the arc reflection method to look through this circuit and very quickly determine where the fault is. And if we look at an example of this, here's a case where we have 3 transformers as part of our circuit, and there's a fault between the second and third transformer. And if we connect a TDR to this circuit, down at the bottom of the picture, you can see the black line represents the low voltage TDR trace. And you'll notice how there's a reflection off of each transformer. And of course, a very strong upward blip reflection at 600 feet at the riser pole. Then if we take our thumper and we do an arc reflection shot where we put a single pulse of energy through this circuit to create an arc at the fault, we'll get a second trace. And you can see the dotted red line represents that second trace. And right where the red V shape is, right where the red trace separates from the black trace, that's the fault location. And even without any distances, at a quick glance at this, I can tell, oh, the fault appears to be between the second and third transformer. Now I can go to that location and verify. Now, this is very simplified diagram. You know, in actuality, the equipment that does this will put a distance on the end of the cable. It will put a distance at the fault, and will also show you distances to the transformers so that you can very quickly see where it's at. So when we talk about fault locating, there is this troubleshooting aspect to fault locating where we can use the arc reflection method to very quickly isolate and do power restoration. And then of course, once we've isolated, say this piece of cable between the first and the last transformer, although now that I look closer at my display here, I see it's labeled the opposite of what I said. If we isolate this cable between T1 and T2, if it was a direct buried cable, we would then fault locate, and where we would actually pinpoint the fault, the exact location. We would know where to dig a hole in the ground and splice and repair that cable. If it was a conduit, we would probably pull and replace it. Okay, so if we focus on the fault location itself, on an isolated cable, in other words, power's been restored, and we're out there working on a direct buried cable, we sort of have a series of steps that we can go through. And one of the steps that sometimes we don't do this, but if you skip this first step often enough, sooner or later it comes back to haunt you. But one of the things that you need to know is where the cable path is. At some point on this direct buried cable, you're going to walk out and listen for the fault and verify, pinpoint the fault. And if you don't know where the cable path is, or you think you do, but you're incorrect, you can lose a lot of time here. So we might consider this to be an optional step, but many times it's wise to do this first step. Then if we look at these next 3 steps, this is kind of the heart, the meat, if you will, of fault locating on a direct buried cable. The first step would be to do a breakdown test, and this is going to verify that we're working on a faulted cable. It's also going to tell us what the breakdown voltage of that specific cable is. And if we have a multiple capacitor, a multiple voltage range thumper, it helps us pick the correct voltage range so that we use enough, but not too much. Once we verified that we're working a faulted cable, oh, there's one other thing, is if you can't verify that you're working a faulted cable, the last thing you want to do is start thumping on a good cable. That would be similar to the problems that you would have on thumping on cable too long for the thumper. All that voltage then comes back into your thumper. You could damage a thumper by thumping into a good cable. So the breakdown test helps you avoid that particular issue also. The second step in the core fault locating process is to pre-locate. And this is where we're going to use the TDR to get a distance. And generally we're focusing on two distances: a distance to the end of the cable. This verifies that the radar signal gets clear to the far end. And then of course the fault distance. And again, this is usually done with the arc reflection method. I know Henning mentioned ice. There was a mention of decay. There are other ways to get pre-location distances, but in the URD world, most of the fault location is going to be done with the arc reflection method. And that's why I call it a distance meter. Obviously it's an impedance measuring device, but what we're interested in is how far away the fault is. Once we've got the fault distance, then we're going to move to the pinpoint stage. And this is where we turn the thumper on in the cycle mode, and it's going to repetitively thump or make noise in the ground. And sometimes we can simply walk out the distance down the cable path and we can clearly hear the fault thumping in the ground. However, many times we need to use that listening device. And again, we've beat it to death, but the right listening device to use is one with the coincidence method, where you're combining an electromagnetic pulse with the acoustic signature. And between those two sensors, we can determine how far away we are from the fault. And then another potentially optional step would be the fifth one here, cable identification. Again, if we're working a simple single phase environment, we may not need to do cable identification. But even in a URD system, the cable identification can be extremely useful. Okay, so let's look a little bit further into some of the tools that we would use. And those three core steps, your breakdown, your distance, and make noise in the ground, they're contained within this tool set, where we have a radar, a thumper, and a pinpointer. Now the radar might be integrated into the thumper, as shown in a couple of these thumpers, or the radar might be a standalone married up to a larger thumper. And then, of course, we have the pinpointing or listening device that uses the coincidence method. Now, one of the things I should point out is the thumper shown there in the middle of the screen and the small thumper down to the left. You'll notice they have identical control panels, and these thumpers basically have the fault locate sequence built into them. So when you turn one of these units on, you don't have to follow this sequence, but the first thing it wants you to do is a breakdown test. After you've verified you're working a faulted cable, a click of the button will automatically take the unit to the pre-location method, where it gives you the distance to the end, and then you give it permission to do an arc reflection shot, and now you have your fault distance. And as soon as you're done with that, it'll automatically scroll to the thump cycle method, allow you to verify the voltage and start the thump process. So that basic fault locate sequence is built into some of these newer units. Now, in addition to this kind of core set of equipment here, of course, you would have potentially a cable locator or tracer. And as mentioned, you could potentially have a cable identifier. So if you add up the pieces of equipment, we have a radar, a thumper, a locator, and a cable identifier for URD fault locating. If we visit just a little closer on the thumpers, again, as mentioned earlier, these come in different sizes. Over here on the left-hand side, we have what Henning referred to as the baby thumper. It's a very small, compact unit. One person can pick it up and move it around. However, because it's small, it doesn't have as much energy level as the bigger thumpers do. In the middle is shown what This is a very common size thumper for URD fault locating. It's still portable. It's easy to move around, doesn't require a dedicated truck, and it has enough energy to get the job done in almost all cases. If you do a lot of fault locating, people start to truck mount these units. On the right-hand side, you can see a truck mount unit. Again, we looked at this picture earlier, but when we start talking about sizing thumpers, you can think about it from a couple of different points of view. One is how much energy does the cable you're going to work take? And Henning mentioned the ratio of the capacitance of the cable to the capacitance of the thumper. So you can do a calculation, if you will, and determine, well, my longest cable that I might fault locate on requires a thumper of this size. That's one way to look at it. The other way to look at it's more from a, how often do I use it? Am I going to use, do I need a piece of portable equipment? Can I benefit from a truck mount system that's where everything is self-contained? So the thumpers obviously come in all different sizes for, for different ergonomics and different cable types. We've talked about the pinpointing and location equipment. Again, here is that coincidence-based pinpointer on the left-hand side. If you look closely at the display, in this particular case, that operator was 33.8 milliseconds away from the fault. Right next to it, you can see the ground sensor with the headset just sitting on top of the handle. If you look in the middle of the picture, you'll see that same display unit, but with some ground probes. And the ground probes would be used for a voltage gradient method, a different technique for finding a fault. You could find a fault in a jacket or sheath of a medium voltage cable, or you could pinpoint a fault on secondary. The ground probes are used when you have a situation where you have, in essence, an unshielded cable. In the case of a jacket or sheath fault, you're basically talking about the jacket itself. A fault in the jacket material. And secondary obviously is unshielded cable. Then looking a little further to the right-hand side is you see the unit that says Ferrolux on it. That's a configuration where you can use this device for cable location or cable tracing. And the orange boxes, the lower one is a transmitter, the upper one's a receiver. So again, that's just another version of a cable tracer or cable locator. Now, if we move on, there's other tools. We've talked a little bit about the cable identifier. Another somewhat common tool would be a high voltage bridge. The high voltage bridge, there's a technique where you can use a bridge technique if you have multiple phases, and you can do a prelocation with this. It has its place. It has it will find some types of faults, give you distance to some types of faults that you can't find with arc reflection. It can also be used for the sheath fault locating. So that's one of the tools that would be of interest in some situations. Looking down at the bottom of the picture, here's the current impulse detector. Henning talked about this type of device. This is what you would use for current chasing in a branched network system. And sort of in the middle of the picture, the black Pelican case unit is our Easy Restore. And I call that arc reflection in a box. Basically, this is a tool where we've reduced the size and the weight down to an acceptable size so that a troubleman can have this tool always on his trouble truck so that he's ready to jump into power restoration using the arc reflection method. And we have to be careful here. This is not a thumper in the sense it won't cycle thump. It's designed specifically for power restoration, And its main advantage is its size and weight, how compact it is so that it can easily fit onto a trouble truck and always be ready to go at the drop of a hat. We move over to the right side. We show a cable ground fault locator. This might be used in an industrial distribution system where, in simplistic terms, we're going to chase a tone down to a ground fault. Down at the bottom is a cable and phase identifier. You can see the 3 clamps. You could have up to 9 of these, and you have a little transmitter box. This can be a very handy way to join cables together. Say you're in a manhole and you want to join A phase to A phase. This allows you to verify and make sure that you're joining the right cables together so you don't accidentally roll a phase. And there's other tools other than beyond this that we could talk about, but that's a quick summation of the kind of the URD fault locating tools, your thumper, your radar, your pinpointer, and then some accessory tools. Okay, one of the things that I'd like to do to sort of wrap up with is talk a little bit about the webinars. You've just sat through one of our webinars on cable fault location, and Megger has been conducting these type of educational webinars, if you will, for some time now. And you can find the recorded webinars at this link, megger.com/webinars. You can find the recorded webinars, and you can also find the upcoming list of new webinars that are going to be available. And then the other type of content that you might be interested in is Megger has produced literally hundreds of videos. And these videos could be application videos. They could be specific questions about specific pieces of equipment. They could be sales videos, et cetera, et cetera. But if you go to Megger World on YouTube and just drill down into the playlists and a little bit of sorting, you can very quickly pick out any kind of educational training videos that might be of interest to you. And then before we move to the end of the seminar and the questions, one of the things that I want to emphasize is, yes, we can tailor a webinar or a virtual training session to your specific needs. We've covered a tremendous amount of material relatively lightly in this webinar. If your company has a specific need where you want to drill down, and it could be an application question, it could be a question about Megger equipment, it could be some more generic question, educational. We'd be more than happy to work with you and develop a webinar or a training session tailored to exactly what you need. And obviously with the COVID-19, a lot of people, a lot of companies, including Megger, we're working from home, we're doing virtual training, we're becoming relatively adept at doing this. And my personal experience is I'm slightly surprised, not completely surprised, at how effective some of these virtual sessions can be if we take the time to set them up, make sure we have all of our technical issues behind us, and we can do some what I would consider to be fairly high quality equipment training and certainly the educational style webinars and videos. Okay, and Michael, I think if you wanted to talk about this slide before we go into questions, or was this supposed to be last?
No worries. This is actually a great slide for me to land on, because for those of you that are about to leave, if you're leaving before we get to our next Q&A session, a survey should pop up on the screen. That survey will have a place for you to request a quote or a demo on any of the Megger products we talked about here today. Additionally, you'll be able to leave comments and feedback on how we did here in our seminar today as well. We love hearing back from you guys. We like to try and make these as enjoyable and as informative as possible. And without your feedback, it's impossible for us to do that to the best of our abilities. So please take some time at the end of the webinar to fill that out for us. We would greatly appreciate it. But moving into our Q&A session, we're going to try and get to as many of these as possible. So I'm going to send the first one over to Robert. Robert, how do you determine where to measure the PK to PK distance on an ICE waveform?
Okay, so pretty much the question, where do you put the cursors on an ICE waveform that you have recorded? Well, typically you put them on, as the question correctly stated, peak to peak. And first of all, you try to find two peaks that are not really distorted, okay? So these ice traces can have various shapes, and you always want to be in an undistorted portion of the waveform. However, you also want to be as much to the zero where the measurement started as possible. However, on ice, you have the phenomenon of ionization time and these things. So never use the first 1 or 2 cycles for that, okay? Because you will have huge distortions and you might suffer from ionization time. What you also don't want to do is be very far to the right on your screen, which means very long into the oscillation. Because of the dispersion effects on the cable, the oscillation is extended over time. So the time from one period to the next is not constant, okay, because of dispersion effects. So you want to be in a very sweet spot as far to the initiation of the measurement as possible, but a good portion away. And when you look at the wave, try to choose like 2 peaks that are not distorted. And typically on ice, peaks work better than zero crossings. There might be exceptions where you say, okay, the zero crossings look better. So that is my advice. Undistorted, not the first 1.5 or 2 cycles because of the distortions and ionization time, and not too long into the oscillation because of the increase in time because of dispersion.
Thank you, Robert. Henning, if the mega ohm test is 100 mega ohms or greater, how do you proceed?
Well, if the mega ohm is a high, basically 100 mega ohm is a pretty good reading, so it would suggest that it's a good cable. But like I was saying, you don't know that for sure because you might use a insulation resistance tester, maybe 500 volt, 1 kV, 2 kV, 5 kV. So if the system voltage is significantly higher, you could miss a fault because at the voltage you're testing, there is no flashover. But if you would go a little higher, you would get a flashover, which would then mean you would see the low resistance. So that's when you get a high reading. It's always the safest way to do a high pot at the peak operating voltage.
All right, thank you, Henning. Marshall, what voltage level do you recommend fault locating using the coincidence method? In which factors of operating voltage does this apply?
Well, let me back into this question. If I understand it right, is at what voltage level is our pinpointing device going to work? And if we back into this question, if we've done our breakdown test, then we know how much voltage we have to use for that particular fault to make it flash over. And of course, the coincidence method relies on the acoustic energy flashing over in combination with the electromagnetic pulse. So if we've done a breakdown test, we kind of know how much voltage we have to use. And Henning talked about this also, but with a multi-stage thumper with multiple capacitors, you can thump at a very high voltage, but many times you don't need to. So if you have your thumper set appropriately for that fault, in other words, I'm using enough voltage, I'm making the maximum amount of noise in the correct voltage range, then in essence, you're set for the coincidence method. By default, you've got your equipment set in the correct position, if you will. If we look at it just from a straight point straightforward point of view. The coincidence method requires that the fault flash over. So as long as it's flashing over, it will probably work. There is an acoustic side to this, though. You are allowed to listen with the headset to the fault. And obviously, if you're making more noise, the headset might pick it up a little bit better. But the fact that you're amplifying that microphone on the ground, it doesn't take very much noise at all to be able to hear it in the headset. So the right way to set, you don't set your thumper up for the coincidence method. You set your thumper up for the fault that you're working. And once you've done that, the coincidence method is going to fall right into place for you.
All right, thank you, Marshall. Robert, Marshall has used the term radar a number of times. What frequency does the TDR use for its pulse?
Okay, here the term radar is an analogy. It uses the same principle, but the propagation happens on the cable, not through air, like an airport radar for the airplanes. So in terms of frequency, the pulse itself, it has a few parameters. It has pulse width and it has amplitude. The way it's shaped can differ from radar type to radar type. Most used is a rectangular pulse, which has advantages for the measurement and everything. Some radars use Gaussian or Gaussian pulses. And these pulses contain very high frequency components and lower frequency components. So it can go up into like megahertz and higher. Now, just to make this clear, this is if you would do certain mathematical operations to that pulse, you could see the spectrum of it and these frequency components going that high. Overall, from a practical point of view, it's more important that you understand, okay, on longer cables, I need a wider pulse because I need more sending energy. I need to send more energy into the cable. You need a higher magnitude, better signal to noise ratio, and also more energy. And another thing is completely independent of that is the sampling of the TDR, right? That also has a frequency, like the microprocessor that works in modern day TDRs, that has a true sampling rate. And that is typically also very high in the megahertz. Let's say topping off at 400 megahertz, for example,
All right, thank you, Robert. Henning, I've heard several times that TDR is ineffective on tape-shielded cables. Can I have a comment on that?
Yes, that statement is not correct in how it's stated here, because if I have a tape shield cable, the tape shield itself works very well with the TDR. The problem with the tape shield is, and if you really look, what is a tape shield? It's a copper tape that is wrapped around the, let's say, the semicon, and maybe half lap. And so when it's brand new, the lap-to-lap contact is excellent because there's no corrosion, no nothing. You have basically like a copper tube, so you get an excellent TDR picture. It's no problem, excellent TDR trace. When this cable starts to age, sometimes what happens is, especially when you have somewhere moisture ingress even under the jacket, okay, then you can have a situation where you build up corrosion between the layers. That's when the tape looks green when you take it off, okay? So now you have corrosion between the laps, and what that means is you don't have a continuous copper tube anymore. Now you have a coil, like a coil that has an insulated wire on it. Once you have a coil, what does a coil do to a high frequency pulse? It kills the pulse. That's what you do when you want to get white noise of when you put a line filter on your unit, you put a coil on to take the noise off, right? So when that situation happens, the radar pulse can be rendered useless, okay? Because it cannot overcome the coil nature of the tape shield. That is very different to drain wires. Drain wires never have that issue, but tape shield can have the issue. And by the way, that is the same issue that you sometimes have on tape shield cable with doing PD measurements, because in the end, it works the same way, right? So, or similar in nature. It is not the radar and the tape shield, it is what happens to the tape shield when it ages. And you never know how badly it's aged. We have one customer, he had a bunch of cables, he couldn't do any radar, and we showed to them, we went on their site and we showed them, using those cables, see, you cannot see, this is all corroded. And then other cables the customer had were fine, so it's not the TDR, it is really the condition of the tape shield.
All right, thank you, Henning. Marshall, what equipment do you use in current method fault location?
Well, we probably should have Henning answer this question since he talked about it, but the pieces of equipment that you would use to chase current, if you will, is you're going to have a thumper, that's your signal generator, and then your impulse detector, your galvanometer, your pickup. I would mention that if someone uses this technique a lot for their particular infrastructure, there is another type of device out there. It's loosely called a thyratron, where it's basically a pulsing current set, and it can provide an excellent method for current chasing. Those are typically like not off-the-shelf items, but that is something that if you're doing a lot of current chasing, we'd be happy to have a conversation with you about equipment that is fine-tuned, if you will, for that method. And Henning, I don't know if you wanted to add anything to that.
No, that's pretty straightforward from the equipment point. It's so.
All right. Well, Henning, while I have you here, if I have one phase of 3 with higher leakage current than others, but not breakdown during high voltage tests, what's the proper action?
Well, so you don't really have a fault on the cable yet, right? It's just you have one phase that has a higher leakage current. So the question is, it will have a potential to fail in the future. Normally, I mean, first of all, if you did this test, I hope you didn't do it on a solid dielectric cable, because you shouldn't do a DC hyper test on a solid dielectric cable. It might have been on a paper cable. And if you did it on a paper cable, then most likely, if you have a higher leakage current, that means you have moisture in the cable, and that creates that higher leakage current. I mean, if it will not blow up when you do the hypo test, and that's what the question implies, it doesn't blow up, it holds, you might be able to find that location if you would do this phase comparison method. You might. I'm saying be careful. I did something similar that was a low voltage cable, 4-conductor cable on a street light, and when it rained, the street light would go out. And when it dried up, the street light came on again. Okay, so it was not a true cable fault, but it was a condition where you create a lot of leakage with moisture. So, and on that particular circuit, I hooked the phase comparison method up, and I was able to see a slight impedance change between the good pairs and the bad pair. And I said, well, that is where that problem is in the cable. It was right in the middle between the two light posts, right? And next time it happened, it rained, light went out, and it blew up, right? And they knew exactly where the fault was. So, like I say, sometimes you're lucky that there is enough change that causes enough change in the insulation, causing that leakage, that it will change the impedance when you measure it, and that way you can see. The nice thing about impedance changes is it gives you not just it's a lower impedance or a higher impedance. Either way is an indication, but it also shows you exactly where that is. That is a big advantage. So, you know, when you measure leakage current, you only know, okay, I can have leakage current along that cable. I have no clue where that is. With the impedance change, I can figure out where that location is.
All right, thank you, Henning. Additionally, if you have a degraded cable that developed a fault, is there any risk for creating an additional degradation or additional faults in the rest of the cable line by thumping the cable?
Well, so you have an old cable, service age cable, that has developed a fault. So I understand this question as, in the course of finding that fault, could you do more harm to the cable? And that question has to be answered yes, because especially if you do fault locate, not using a TDR, just thumping, and you have to thump for a whole day on this cable, you might push this cable, one of these other spots that are very close to fail, you might even have pushed it closer to real failure. So, you know, an old cable, that's why you try to minimize the thump time on cables, okay? And I mean, sometimes we use, actually, when we don't have a, you know, we need to condition the fault, like you have a wet cable. Take that example, okay? You have a wet cable, doesn't flash, so you thump it a few times, you condition it, now it thumps, right? So you can, and if you had a cable that has an almost a fault, and you thump it a few times, you might fail it because now it's a pinhole, okay? So that can happen, okay?
All right. Robert, how long have multi-capacitor thumpers been around?
Okay, they have been around for a long time. You know, the arc reflection method was pioneered in 1965, and shortly after, that company that you know, did all this, called HDW from northern Germany, they also started building the first multiple stage capacitor thumpers, and it all started like little and cute, you know, a few hundred joules in 3 kV, 6 kV, 12 kV, and then you know, these things you know, evolved into bigger units over time.
All right, good deal. Additionally, Robert, in regards to ice, how many blips do you recommend to get a clear reading? I know you need to play with the gain, range, and voltage to get a better picture. What's your opinion?
Okay, so I give you like a proper engineering answer. It depends. It really depends on the quality of the trace and how it looks. There are traces that are simply very distorted in the beginning, and some other traces are cleaner. Then you have traces with like some, bumps in the fundamental oscillation that you see. I'm not saying all of the like every trace is unique. I mean, they show similarities, but you cannot really say, okay, if you do ice, the fourth blip, that's where it is. You simply cannot say this. I give you one word of advice. Again, look at the trace, how good the oscillation is, that you have a minimum of distortion. It should really look like an oscillating signal that you captured. I guarantee you the first cycle, the first 2 cycles maybe, are always like distorted or heavily distorted. Sometimes you have these long ionization times. So you have to find a spot where you can clearly see the oscillation. In terms of playing around with the parameters, the most important one is the let's say the X range. Okay, the measurement range of your oscillation, because as you heard, you have to be 5 to 10 times, preferably 10 times the cable length, to capture the full oscillation, to actually see where the best place could be to put the cursors to. So one common problem that I sometimes see in the field is that people see a very distorted trace and they don't know what to do with it, and then you realize, wow, the cable is 3 miles long or 5 miles long, and their range, like the distance that they have on the screen, is only a few hundred yards or something like that. So they don't even see the full trace. So the most important adjustment is the X range, as it is called with our TDRs. So you want to have minimum 5 times of the cable length to actually see that transient, that traveling wave, really. And then again, don't try to do it in the beginning because the nature of the ice trace, and don't do it far away either. So let's say if you have a cable that is 2 miles long and you set your X range to 20 miles, don't measure like 18 miles in, okay, because the oscillation will diminish. You have losses, and as I said, because of the dispersion, this oscillation time is not constant. A lot of people think that, but it's not. So you should be as early as possible when it starts looking nice, and so don't try to pinpoint it on one spot that you can always use. It depends on the situation, how good your trace is.
All right, thank you, Robert. It looks like that's all the time we have for our question and answer session. We apologize if we didn't get to your question today, but we will be following up with you offline in the following week. I'd like to thank you all for attending. If you could, please remember to answer our survey. We would greatly appreciate it. That survey will also include a field for you to request a quote or a demo if you're interested. A copy of these presentations, certificate of attendance to the seminar, as well as a link to the video recording will be sent to everyone in about 2 business days. Our next webinar will be tomorrow at 1 p.m. Central Time. The topic will be case study and field experiences, sweep frequency response analysis, and it will be presented by Volney Naranjo. You can register for this and other webinars, as well as previously recorded webinars at our website at us.megger.com/webinars. But once again, I'd like to thank you all for attending, and I hope you have a wonderful day.